So I hope you're building up some kind of a fluency to say, if it's a significance test, I'm using this kind of generic formula. If it's a confidence interval, I'm using this generic formula. I know kind of some of the things to look for, and we'll hopefully clarify that even more. But if it's one sample or two sample, then I know where to go to fill in the generic formula with specific variables. And then once I've got that, then I can find my specific values to plug in. And the only thing that changes a little bit, besides the specific values to plug in, sometimes with the two samples, there's a little bit of nuance with the conditions, checking the conditions. So you have to make sure you kind of like the big one being, if you just to do a flashback here to the two sample Z test for two difference of proportions. That's where you're not using p hat sub 1 and p hat sub 2 anymore. Now you're using p hat sub c. So there's a little nuance that gets thrown in. Okay, so that can be, but besides those things, I hope you're kind of figuring out, okay, it's just more of the same. The process stays the same. And at least for me, and I hope for you, it's just building on itself and you're feeling like you're getting the hang of it. So having said that, let's see if you guys can, I'm probably just going to run through this, but on your own, I want you to see if you can kind of anticipate what's going to happen as we run through this problem. Some of it you'll anticipate, some of it you might not. But I think you'll anticipate pretty much all of it. All right, so let's jump into it. According to a Stanford Business article, Americans may eat fewer calories at restaurants if the calories of the food items are labeled on the menu. To investigate this, researchers compared Starbucks receipts from locations where the menus were labeled to receipts from stores where the menus were not labeled. A random sample of 30 receipts from stores with the menus labeled had an average number of calories of 225 with a standard deviation of 100. A random sample of 40 receipts from stores without menus labeled showed an average of 265 calories per receipt with a standard deviation of 75. Does this provide convincing evidence that the average calories per receipt at Starbucks with a labeled menu is less than at a Starbucks without labeled menus? Okay. So, well, what's our parameter? What is what is it about the population that we're trying to make inferences on?
If seeing the number of calories makes them buy more or less. Well,
yeah, and that's kind of the verbalizing it, just kind of describing. But statistically speaking, how would we write that out as a parameter?
Maybe the parameter, the average number of calories people eat when they don't see the menu is minus when they do. Maybe that way around.
Yeah, and that's good. So Leo was kind of saying it's basically your the mean calories from when you do see the calories on the menu versus when you don't, subtracted, those two means subtracted. And honestly, it doesn't matter which one is first or second. And in that case, I tend to go with the first one that they tell me as the first sample. Okay, so in this case, the random sample of 30 receipts was for menus labeled menus. So in this case, my mu sub 1 will be the labeled menus minus mu sub 2, which will be the unlabeled. So to put that back into just a phrase, everyday language, we could say the true difference between mean calories from labeled menus minus unlabeled menus. So if you guys can actually read my writing when I put it up on the screen, you're amazing people. But all right, so that's what we're going to make some inferences on. We are using a statistic that comes from our data, and this is one where you can just kind of anticipate it. We don't know the true population mean in either case here, so we're going to be using our sample means, in which case I can find the sample mean, or I don't have to find it, it's given. So the sample mean from the labeled is 225. Maybe I could do this up here in the corner. I could say x bar sub 1 is 225. S sub 1 is 100. And again, if you're kind of going back and forth to the prompt, you can find those numbers there. It does say standard deviation. I will say this, every once in a while, just because sometimes question writers are just jerks. Every once in a while, they will, instead of giving you standard deviation, they're going to give you the variance. And so sometimes it'll say with a variance of blank. And, you have to watch out for that, but that's not the case here. All right, the next one. Now I'll also say the sample size for the first one was 30. So then we can look at the next. The sample mean for the second was 265. The standard deviation for the sample standard deviation here is 75. And the sample size for the second is 40. So those are going to be the numbers that we need to know. So x bar sub 1 minus x bar sub 2 is really just going to be those straight up numbers there. It's 265 equals negative 40. And with that, now it's negative 40 calories. We're good with that. Hypotheses. We need to know the null and the alternative hypothesis. And do you have an idea of what our null hypothesis would be here? There is no difference. Yeah, so how would we write that? That's it. Okay. It's okay. It doesn't work anymore, remember?
Yeah, you broke it. I was just touching it. I don't know.
It's finicky. All right, so then the alternative here, mu1, and we're dealing with the parameters. So we can always, I don't want to put anything there yet. Notice that we're drawing inferences and making hypotheses about this parameter. So that's going to give you a clue. That's always, that parameter equals 0 or it's greater than or less than or not equal to 0. So to determine, first of all, if we're using not equals or not, let's read the question at the very end. Does this provide convincing evidence that the average calories per receipt at Starbucks with a labeled menu is less than at a Starbucks without labeled menus? So we know it's not going to be not equals to. We're definitely looking for a specific direction. But the way that we labeled ours, are we looking for this difference to be less than 0 or greater than 0? Okay. All right, so we would want the mean, since we decided that that mu sub 1 equals, what does it equal? It equals the calories from a restaurant with menus labeled. Okay, so we want that to be lower, so we want 2 to be bigger if this hypothesis is true. Therefore, when we subtract 2 from 1, it will be less than 0. Okay, and the significance level here, what are we going to go with? Trusty old 0.05. All right, and honestly, in this class, we don't get into the nitty-gritty details of why you might choose a 0.05 versus 0.01 beyond the kind of questions that you've already seen. We know how this impacts your type 2 error, your power of your test, and things like that. But in a specific context, we don't get into why would it be better in this case to have a specific significance level. And that's something that we'll get into in more, or you would get into in more detail if you're actually doing research and figuring out an appropriate significance level. All right, enough on that. Let's look at the next part. So the actual, I've never made a big deal about this, but notice it says state, and then the next one's going to say plan, and then do, and then conclude. If that framework, if that structure is something that you can remember, state, plan, do, conclude, then that's just a good mnemonic to help you make sure you cover everything. But now, notice here, I'm just going to let you read through my writing. The null hypothesis for means is that the difference equals 0, or this. So that's it. Now we can talk about the name of the procedure. I'm going to leave some of the stuff up so you have some of the variables given. All right. Maybe I could keep that. Oh, well, I erased it. I can't go back. All right. I know this takes a little bit more time to get rid of this, but there we go. The name of this procedure. Does anyone think they know what this procedure is going to be called?
Two sample t-test.
That is good. Two sample t-test. And this would probably be sufficient to show what it is. If you want to give a little bit more detail, and something that would certainly be good, two sample t-test for mu sub 1 minus mu sub 2, which is a way of saying a difference of means. All right, so that's just a little extra there. Though I will say this, I finally caught up with grading for everyone. So your grades in Student View at this point are completely up to date. And having said that, sometimes some of you have been writing too much in your answers. You have to be careful. It's not a problem on its own to write too much. It's a problem if you write a lot and then somewhere in your long paragraph, you end up writing something incorrect. So you don't want to write so much that eventually you say something incorrect, because then you will be counted off for it. So you want to try and, it's a careful balancing act between writing enough and not writing too much. So I don't grade very harshly on the AP test. You know, I don't know how the readers would handle it. Maybe you only lose one of your points. Instead of getting a 4, you get a 3. Maybe they grade very harshly. But anyways, typically you would lose some points if you say things incorrectly. So enough on that. That's probably clear enough. So remember checking conditions. And even though we haven't done this test yet, I asked you to kind of anticipate things. So if we're looking at the first one, if we're looking at our conditions, the conditions are still the same, except now we have to check it for 2 different samples. We want to make sure they're random. We want to make sure it meets the 10% condition. I could ask you to name these, and hopefully you could. And what's the last one? Central limit. And specifically when we are doing that, we're asking if it's normal, approximately normal. Okay, but we would use for means the central limit theorem. So first of all, are these 2 samples random?
Yes.
Okay.
It says random.
It says random. So here's where you could write random sample. By putting it in quotes, you're saying this came from the prompt itself. And the only thing I'm going to do real quick, I'm going to change this to X bar. All right. And the next one says random sample. So I'll show that. %. You have to think for each sample, what's the population? And are we less than 10% of the population that it represents?
There are probably more than 40 or, sorry, the better way of saying it is that there's, I can't speak.
You're on the right track, but that's okay.
I know what I'm trying to say. It's just not.
Okay. So we had a sample of 30 transactions from stores with menus labeled. Do we think that represents more than 10% of all the transactions that happened? No. I think it's safe to say that is less than 10%. So you could write this a number of different ways. Just make sure you don't just put a check mark here. And I know I do that sometimes. That's whenever I'm trying to get to a different kind of, I'm emphasizing something else. But in the real thing, I would want to say 30 is less than 10% of all transactions. And yeah, transactions at stores with menus labeled. And then the same thing for 40. And you don't have to say it this way, just make sure you're not just putting a check mark. All right. And lastly, normal, you mentioned central limit theorem. Have we met the central limit theorem?
Yes, there. Yeah, 30. 30 is equal to 30. 40 is greater.
There it is. So n is greater than or equal to 30. N is greater than or equal to 30. So we've met both of those with the central limit theorem. Now, one thing we had to do with the difference of proportions is we had to pool our data. And there is such thing as pooling data for means, but in practice, we never do it. So I just want to point out, just in case if that's in the back of your mind somewhere, like, wait, why don't I pool data here? The only way we pool data is if we have reason to believe that the variance or the standard deviation, either one, that the standard deviation between both samples is the same, or between both populations is the same. So that we would only use pooling when we assume that both populations that we're comparing have the same spread, same standard deviation. We don't make that assumption ever in this class. So just in case that was on your mind somewhere, we don't pool, we don't have to worry about it. It actually makes it a little more straightforward. Okay, so we're good with checking our conditions. We're good to go. So let's do some stuff. All right, you get to watch me erase my screen. How cool is this? I don't know if you're the kind of person, whenever I watch teachers erase their dry erase, and they missed like one little mark, it just bugged me, and I couldn't pay attention to what they were talking about after that. So maybe you're the same way. All right. I'm not worried about the mean and the standard deviation. That's just helpful for setting up what our model is, but we're going to basically draw our model, and we're going to include the mean and standard deviation whenever we get into our specific formula here in a minute anyway. So the general formula for any hypothesis test is you're going to have your test statistic equals the stat minus the parameter divided by the standard error. That is on the AP formula sheet. You have been using it. It's essentially a z-score. The specific formula for a difference of means, a two-sample t-test for a difference of means, what do you think we're going to have here? I'm going to let you guys kind of anticipate this. So what letter am I going to use for my test statistic? Close, just T. Yeah, T star would be the critical value for confidence intervals, but you are right, it is going to be a T statistic. All right, what's my stat? That's the number that we're plugging in. What would it be kind of with,
No letters.
yeah, with the,
X1 minus X2.
there it is. X bar sub 1 minus X bar sub 2. All right, so then it's minus the parameter. What's the parameter in this case? I'll give you that hint. Yeah, in this case, it's mu sub 1. So we'll plug in the numbers in a second. But it is good to show the specific formula so that, the last thing that a rater wants to see, and that includes me, is just an answer. Because how do I know how you got that answer and that you really know what you're doing? Did you just plug numbers into your calculator and your calculator said, here's a number to write down?
No, it's just divine intervention.
Oh, or divine intervention. That can be the,
God in my hand. That really helps somebody. I'm gonna write that. I'm gonna write the answer.
Hang on, aren't you in math in my class? Divine intervention.
just divine intervention everywhere. Okay, now on your formula sheets, I want you to find the standard error for a difference of means. Tell me what it says.
All right. Let me do a formula sheet.
No.
I'm an animal.
All right.
You will learn to take care.
Next time I do my homework, I'm just gonna say, Eli ate my homework.
All right. Did anyone
That's how
find the standard error expression?
Oh boy. So, where's yours? It's S over root n. No, wait, no. It's there's. Do you want me to read it all out? It's the root of S sub 1 squared over n1 plus S sub 2 squared over n2.
There it is. Perfect. Those are twos right there. A little hard to read. But again, and I know some of you were finding this at home and maybe just weren't talking, but first of all, the middle part of that back is telling you it's for sampling distributions for means. And you come down to 2 down here, you can even see it shows you your difference of means. You come all the way over to the far right column, and you can see your standard error. So there it is. Okay. So we've got this. We've got the specific formula. Now we can actually plug this in, and that's why I kept all these numbers. Now it's just really plugging numbers into an equation and letting the calculator take over, as long as you use the calculator correctly. So actually, I'm not going to plug numbers in. You guys can do that. Let's just figure out what the test statistic is going to be, your t-value. All right, so just to show this, and I know some people might still be coming up with their test statistic, I'm just going to start plugging in specific numbers into our specific formula so we can see what we should have been calculating. So it's -40 minus 0, because our mu sub 1 minus mu sub 2 is always going to be 0. And then the square root here is going to be, that's 100 squared over 30 plus 75 squared over 40. So it's easy to, if you try and plug this on your calculator at once, it's easy to make a mistake. So whatever you need to do, you can find the number. Again, I got -1.837, and then so on. Okay, so that's all well and good. And what I wanted to do before we just find the p-value, it's good to draw the picture. So I'm going to go ahead and draw this. This is our t-distribution. And what we're going to assume is that there's no difference between these two samples. And we have a standard error, or there's no difference in the population. So there's the null. With our standard error, what we're doing is creating a sampling distribution that says, okay, one standard deviation away, we're going to be, we're going to have our z-scores. Anyways, I don't know what I'm trying to say with this, except that our standard error is represented by this distance. Okay. So we are at a negative, this is 2, we're at a negative 1.84 test statistic. And so we want to figure out the probability of getting that value or more extreme. And this is where, okay, so we have the test statistic. I'll write it in negative 1.8. I'll just keep it at negative 837. So we get a little bit more accuracy. It's not going to change our answer by much. And remember, with this part of it, we don't need to go to the t-table. I will direct you there now if you have a reference sheet available. If we look at our degrees of freedom, and this is not going to work out perfectly. All right. And let me see. But it's going to work out close enough because this is all very rough when you go to a t-table for this. So first of all, the degrees of freedom, we're going to keep it very simple. Just like we did yesterday, our degrees of freedom is going to be the lowest sample size minus 1. So that's going to be 30 minus 1. So we're going to go with 29 degrees of freedom. And what I'm going to do is, if you wanted to use a table, and actually you're going to find out it's way easier to use a calculator, like it is in a lot of cases. But if you were limited to it and you had to on the test, they do give you the tools you need to do it without a calculator. 29 degrees of freedom. I'm going to go over until I find where the absolute value of my test statistic falls. And I will, if I look at this at 29, it falls between the values 1.699 and 2.045. All right. I don't know exactly where, but all right. So if it's hard for me to do this at the same time.
I'm not seeing those.
So it's on the row for 29 degrees of freedom.
Yeah.
And you keep going over, our test statistic is negative 1.84.
Yeah.
Now, get the absolute value of that is 1.84. I'm going to go over until I find where that would fall in line. So 1.84 falls between 1.699 and 2.045.
Okay.
So I think I'm pointing to it now. So it's going to fall between these two. Now, what does that mean? If I go up to the very top of this column, notice it says the tail probability up at the top. And so that's 0.05 up there and 0.025, if I'm reading it correctly. Yeah, so 0.025 and 0.05. My p-value is going to fall between those two. That's as accurate as I can get it. Now, in a pinch, let's say your calculator goes out on you in the middle of the test. You can't recharge it. You can still get this done. We can do better than that if your calculator is working. Are there questions on how we used the calculator or how we used the t-table there? All right. Well, the faster, simpler way to get an exact p-value is to use TCDF. All right. So I will go to second and distribution. TCDF is option number 6. There are 3 parameters to plug in. I need to plug in where my cutoff points are. So my lower bound is going to be negative infinity, and I'm basing that on my picture that I drew. So I'm gonna go from negative infinity up to negative 1.84. And my degrees of freedom on this will be 29. That'd be. It should look something like this when you're about to plug it in, when you're about to calculate it on the screen. And depending on how much precision you did for your lower bound, or your upper bound rather, you're going to get something close to this. You might be slightly different in the exact decimals. So I got 0.038 when I did negative 1.84. If you did negative 1.837, maybe the thousandths are off or something. I don't know. So what we were able to find by using the t-table is that the p-value is going to be between 0.025 and 0.05. What we found by using the calculator is exactly, it's 0.038. So this represents the p-value. Okay, so before we actually write it out, what's our conclusion? We reject the null hypothesis. And what does that mean in our context?
That there's no convincing evidence that people will eat less calories at the store where the menus are provided with the calorie amounts.
Close, except exactly the opposite.
It means we reject the null hypothesis because so that means that menus that are unlabeled, people tend to purchase more calories. I don't know, I'm saying that backwards, but people